Hello, my name is Will Simonson, and today I'll be going over Lab 5 covering magnetism and Faraday's Law. So first, for the introduction, Faraday's Law, it describes how magnetic fields changing generates current, and it is shown in this lab through dropping a magnet through an aluminum foil tube with gravity acting on the magnet. And so the results experimentally, which was in class using video to time this occurrence, was an average of 1.662 seconds, while the average time mathematically was 2.436 seconds. So the fundamental equations that were used in this lab were Newton's second law, force is equal to mass times the acceleration. Also, technically, Newton's third law, where a force is met with an opposite and equal force, and that's because of the flux or the EMF that's generated, or I guess the current that's generated due to the changing magnetic field. And so for Faraday's law, we have EMF is equal to the change in flux over change in time, which is equal to the integral of the electric field times the change in length. And then Biot-Savart's law, which is mu over 4 pi times 1 over r cubed, and all of that multiplied by 3 times mu times r minus mu, and magnetic force, force of magnetic is the 12 pi r times the absolute value of the magnetic field times the sine of theta, and then the change in flux over change in time is shown by this equation, which is changed by the distance from the two objects and the radius. So some experimental considerations: negligible air resistance, gravity, magnetic force are the only forces. The system is aluminum and the magnet. The surroundings is everything else. And for the procedure, we made sure we knew what the magnet's north was, and then dropped the magnet 5 times and recorded the time it takes to pass through the tube. And so sources of error were timing from the foam, maybe not enough frames to capture the exact time, or the tube not measured correctly. And so there's a lot of code in this experiment. So initializing some variables shown on the left, and then in the right we initialized the tube and normalize some variables for our loops. So more code, we have creating the electric field parameters of the tube, calling it like a ring, and then making sure we know the change in flux. And now we're going to find the magnetic field at each ring, so we can calculate the change in magnetic flux. So we can then calculate different variables shown in the equations that I talked about earlier. So the model you can see right here, the red is the magnetic field, the current being generated within the tinfoil. And so you can see that because this current counteracts the magnetic force, it's going to act in an increased direction, and the velocity, which once was accelerating, or decelerating technically, getting more negative, and then because the flux opposed it, it started to accelerate. And so for our what if questions, we have what if the resistance corrector was reduced as close as possible to 0? How the dynamics of the falling magnet change? So near zero resistivity calls for a near zero resistance, but the smaller resistance, the larger the current, so the current would increase. And the magnetic force would increase, and this force counteracts the bar magnet. And so the next what if, they would decrease the induced current, which would decrease the magnetic force, which counteracting it, making the force of gravity having more of an impact, and the magnet falls faster. Thank you.